We will start the new chapter, relations. Some mathematicians describe mathematics. Relation is a set of order pairs, and we get our glimpse of the fundamental importance of the concepts of an order pair. So you should note these 2 points. Some mathematicians describe mathematics as the study of relations. A relation is a set of ordered pairs. Set of ordered pairs. Let's start with the definition. 1.3.1. A binary relation or simply a relation or from a set A into a set B is a subset of the Cartesian product of A cross B. Now, a property let R be a relation from a set A into a set B if x comma y is in R. We can write it as x is R related to y, or R of x is y. If A is B, then we speak of a binary relation on A. Let's talk about applicative example. let A denotes the names of states in USA. B denotes is it the positive integers or the integers. Now with each state A in A, associate an integer n, which denotes the number of people in that state during the year. Number denotes the number of people in that state in the year 1996. Then we can say that R is set which contains A comma N, given that A in A and N is number of people in the state and year 1996. Then R is subset of A cross Z. Thus, R is a relation. R defines a relation from A into Z. R defines a relation from A into Z. We can give another example. Consider the set of integers Z. Let R be the set of all ordered pairs m comma n of integers such that m is less than n, i.e. R will be a set which contains all those ordered pairs of the integers from Z cross Z with the condition or the property that m is less than n. then R is a binary relation on Z. Definition. Domain of R, image of R, let R be a relation from a set A into a set B, then the domain of R denoted by D of R is defined to be the set X such that X is in A and there exists Y in B such that X comma Y are in relation R. Similarly, the range or image of R denoted by I of R is defined to be the set Y such that Y in B and there exists X in A such that X comma Y is in R. And this is when image and range both are same. Image and range can be different. And we will talk about that by the example. So let's say we have an example that we have a set A, which has 4, 5, 7, 8, 9 elements. We have a set B, which has 16, 18, 20, and 22 elements. 22 as an element. Let's say which one will be more visible. So probably why it's not this one. This one could be visible. Yeah. So we have R is a subset of A cross B R have following order pairs, that it is 4, 16, 4 goes to 16, 4 goes to 20, 5 goes to 20, 8 goes to 16, and 9 goes to 18. Remember, R is a relation, not a function. So forget about the definition of function. This goes here. This also goes, 4 also goes to 20. And then 5 goes to 20. And then 8 goes to 16. It goes to 16. 9 goes to 18. And we have missed one. 7 goes to 22. Okay. Then the domain of R is 4, 5, 7, 8, 9, and the image of R is 16, 18, 20, 22. And then range of R is same as image of R in this case also. Okay. Now, let's talk about another example. Which says that let S be a set of order pairs such that they are real and they satisfy this equation. The equation of circle such that y is greater than 0. S is a binary relation on the set of real numbers. S is the set of points in the Euclidean space or plan constituting the semicircle lying above the x-axis with center 0, 0 and radius. Then we have types of relations. So definition 1.3.7. Let R be a relation on a set A, then R is called one reflexive if for all x in A, x is R related to x, x is related to x, by R2 symmetric, if for all x comma y in A, x is R related to y, implies y is R related to x. 3. Transitive. If for all x, y, z in A, x is R related to y and y is R related to z, imply x is R related to z. Perfect. Then we have another definition about equivalence relation 1.3.8. A binary relation E on a set A is called an equivalence relation on A if E is reflexive symmetric and transitive. And this is very important. And this was given by Gauss. Let's define this by an example. So we have a relation, we have a set A, which is 1, 2, 3, 4, 5, 6. We have a relation E, which is between 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And it says that 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5, 6 goes to 6, 2 goes to 3, 3 goes to 2, 2 goes to 3, and 3 goes to 2. So 2 and 3 are going to each other. And then we can write this also, that E can be written as 1 comma 1, 2 comma 2, up to 6 comma 6, and 2 3 3 2. Then we can say that E is an equivalence relation. Talk about another example. Let's say 1 L denotes set of all straight lines in the Euclidean plane. L is in the Euclidean plane, and see the relation on L. Relation on L defined by for all L1, L2, L of L1, L2 belongs to E if and only if and only if L1, L2 are parameers. Then E is equivalence relation on L. Equivalence relation on L. They are not parallel, they will not satisfy the condition of symmetricness and the transitivity. 2, L defined in 1 and P be the relation on L P be the relation on L by for all L1, L2, right, the L of L1, L2, which is inside P, if and only if L1 and L2 are perpendicular. Late L be the line, and capital L, since L cannot be perpendicular to self. So this L, comma L is not inside P. Hence, P is not reflexive, and so P is not an equivalence relation on L. We should know that also P is not transitive. It is enough to show for a single line. Example of very interesting kind. So 1, 3, 1, 1. We say we have relate n be a fixed positive integer in Z, set of integers. We define a relation on Z by for all x comma y in integers x and is y if and only if n divides x comma y, i.e. x comma y is n into some k for some integer k. We now show that this is an equivalence relation on Z. Show. So solution. Number one property that for all x and z, comma x is 0, which is 0 into n. Hence, for all x and z, x equals is this relation is x. Thus, this is reflexive. 2, which we show the symmetricness. So we take two integers. Suppose there is this relation between these two, then there exists q in the integers such that qn will be x minus y, plus minus qn will also be y minus x, and so n divides y minus x, i.e. y is congruent to x. Hence, symmetric. If three integers, suppose x relation to y and y z, not this z, small z, small z, and here exists q and z, not only q but r also. Q and r and z, such that we can write qn as equals to x minus y, and rn is equals to y minus z, as we can write q plus r into n is x minus z, and q plus r is also an integer, so consequently yeah, we end up with x is this to z, hence transitive C2 in general. This is equivalence relation. Just a quick remark. This is called congruence modulo. We also write this as x congruent y. We will end our lecture of this part here.